Okay, lecture 13 is extension of the geometry and mechanics of lecture 12. And we have already done an introduction to the Lagrangian mechanics using the generalized curvilinear coordinates. And so this first part here will mostly be concerned with the Hamiltonian's approach. The Lagrange, as we have shown at the very end, likes to make a Hamiltonian using a covariant metric, which then matches velocity components, which have their indices up according to Riemann.
Before we proceed further, could you once again say what is the formal definition of a scalar, vector, and a tensor?
The formal definition of a what kind of vector?
Any a vector, say, such as a magnetic field, any vector like xi hat plus yj hat plus zj hat, the way we define.
Maybe like the x1, x2, and x3.
Yeah. Such as momentum.
The easiest definition is simply coordinates. Coordinates of something. It could be coordinates that are keeping track of velocity or acceleration. So it's a multiple thing to take care of something that has more than one dimension. So you define a vector already just with two dimensions, as we've been doing here, just x and y, or q1 and q2, q super 1 and q super 2, the contravariant coordinates of Riemann, which we're basing everything on. Then a tensor is just a vector-vector. I mean, that's a very flippant definition of it, but a matrix can be looked at either as a collection of columns, and each of those columns would be what we would in quantum mechanics call Ket vectors, but here we call them the contravariant vectors, or coordinates make components of vector. So the other side of the story that isn't usually taught that well, certainly in physics, is the rows of a matrix. That's a collection of the, in our case, covariant vectors, or bra vectors. Vectors that like to be acted upon from the right side by a matrix. It's an operator of matrix. And then here is a bra vector which has a flat side. The flat side is where you make contact with the matrix operator. Okay? So that would have to be a row vector in order that I can multiply the way I multiply matrices to get each of the components of the transformed covariant or bra vector. Perhaps we could turn the lights on and remind ourselves, since this course is supposed to be getting you ready for really understanding quantum mechanics. If you look at the very first set of ceiling slides here, this is a typical transformation matrix that Feynman would define in his volume 3. And you can see I've indicated the columns of the matrix, the transformation matrix, by Ket 1 prime, Ket 2 prime, Ket 3 prime, which occupy the right-hand side of what are called amplitudes, but they're scalar products for a mathematician. And you can see every one of these has a 1 prime that sits above the 1 prime Ket. So that whole column there is a 1 prime Ket. And that's the contravariant in our Riemann deconstruction. And then you look at this row here, and this one, and this one. The first row, you see, has 1, 1, 1 as the first number in the scalar product, and that, of course, is a bra that sits on the left of a ket, and the scalar products are brackets. And so that whole row there is a number 1 bra. This whole row here is a number 2 bra, and so forth. Okay, so the bras or rows and the kets or columns are quite analogous to the duality that we have for the vectors that are covariant and contravariant. Does that help at all? This is a sea of weird sort of definitions that work very well. Some of the most powerful notation that has ever been devised by physicists, and then borrowed by mathematicians. They have bras and kets too, they just don't put the points on them. They're rounded, they use parentheses. In most of the books I've seen. Okay, so you may have been asking another question than that, but the basic idea, go ahead and flip the lights back to the normal level. It'd be on the extreme right there and hit the extreme left, little switch there. Both of them. See if you can hit one. There you go. That did it. Thanks a lot. So it's the contra that occupy our Lagrangian because it's a function of velocity. And in order to balance two of those in a quadratic form, we need a covariant metric tensor. That's a matrix. Okay? Our matrix is very simple because it was diagonal for polar coordinates, but it's not going to be that way for any of the stuff we do after this review, Unit 1.
Dr. Harter, the matrix that represents the metric would be diagonal if the space is flat, right?
It's better to say it would be diagonal if every coordinate line meets every other coordinate line at a right angle. That is, if it's an orthogonal coordinate system. It doesn't matter what it does after that. It can be very curved. The lines of the phi equal constant are circles. And in polar coordinates, you have spheres and cones in addition to planes in three-dimensional polar coordinates. So it's not so much curvature, it's rather the relationship between the coordinates. And we want to be able to do coordinate systems that are like that. So most of our mechanics coordinates would be like that. So this is diagonal because the scalar product of 1 with 2 is 0. And that's what these things are. They're the measure of the scalar products of the covariant vectors. Now, this guy's the measure of the scalar products of the contravariant vectors. And that's the one that's going to be matched to momentum, and momentum is covariant quantity. So that's what we're going to do today, is look at the Hamiltonian as a point counterpoint to the Lagrangian, and see how their equations relate, and why it has to be expressed in terms of momentum. And you do the polar coordinate example, and show that the Hamilton's equations are very convenient in a practical sense. They're immediately in what's called Runge-Kutta form, so that you can just feed them into a computer that can do the Runge-Kutta integrations. Numerical analysis loves Hamiltonian equations. The Hamiltonian mechanics with the polar coordinates and effective potential, I'm going to show the Coulomb orbits too, but we're going to do the harmonic oscillator that comes with our sophomore physics Earth inside as well as outside. We'll show some simulations there. Now the effective potential, I point this one out just for the as it affects the graduate qualifying exam. in mechanics is almost always a problem involving an effective potential. And so that technique, which works really well with Hamiltonians, not so well necessarily with Lagrangian, is important. And the effective potential theory, which we'll go over in more detail later, I just want to get you introduced to it in this review unit. It's something that you should have had in an undergraduate class, but not always. Just out of curiosity, how many times did you see an effective potential in your undergraduate education?
Nothing. I never had. This is my first course in mechanics.
Okay,
I never
so-
had mechanical
so
engineering.
You would you would miss it by default.
Yeah.
And
Yes.
effective potential is something you saw in a
Yes.
earlier class. So this will be old home week for you. You'll enjoy seeing the graphics that go with it, though. Now, I'm going to say a few things about envelopes. If we get time, we'll see how things are going. And I also want to look at phase plots. That's the thing that Hamiltonian's really known for. So if we have time, we'll do that. But there's some pretty heavy algebra in this, which I don't want to rush. So I would like to just quickly go over what happened last time. And I'll put that on this screen right here. This wasn't last time, it's time before last. But the idea of having differential equations with partial derivatives that are identically zero will show up here again. And this is where we will also get the Legendre transformation, the Poincare combination or transformation between Hamiltonian and Lagrangian in a very algebraic way. We've seen some of the geometry of that here. The first equation of Lagrange and the first equation of Hamilton involves defining the momentum in the case of Lagrange and defining a velocity as a gradient in terms of the Hamiltonian. It's the other equations that come non-zero when there's a potential or other forces on a system. So just to remind you of all of this, we have the Lagrangian here written as a 1/2 mv squared, v dot v, or r dot is the kinetic term, and then the potential is just a function of coordinates, not the velocities. And therefore, we have a 1/2 m covariant metric, contravariant velocities, q dot m and then q dot n summed over all m and n in general, but in our case, the metric tensor or matrix or coefficients are zero off diagonal. They're just equal to 1 for the first component, the radial component, and they're equal to r squared for the angular component. So this is the actual Hamiltonian, I'm sorry, Lagrangian, I'm getting ahead of myself. The Lagrangian is a sum of r squared and r squared phi dot squared. This is r dot squared, I'm sorry, and this is phi dot squared multiplied by 1/2 of the mass. So that's the thing out of which we could produce immediately a radial momentum. No surprise there, but this was a nice thing of getting angular momentum with the inertial, rotational inertia just given to you mathematically. Then the equations of motion for P dot R, that is a partial derivative of L with respect to R by our second Lagrange equation, okay? And there's one for R and one for phi. And the main thing that was very interesting about this was that we also get centrifugal forces sort of for free. This is center fleeing force, which we can relate from the previous equation for PR dot, and we see here that part of it, and then the Coriolis is coming out. All of the Coriolis effects, so-called fictitious forces, due to the curvature of the coordinates. Coordinate vehicle constant is curving, but then the radial quantities are also being met. And then the Coriolis forces the effect on our weather. I hope you enjoyed the nice cool wind that came the next day after this lecture and broke the summer heat very nicely. And we can expect to see some more of those things making us even colder as the season goes on here. So this sort of mathematics needs to be related to the Hamiltonian mathematics. So that's what we're going to be doing here. So I'm going to go ahead and skip this part of the thing and get started on deriving Hamilton's equation from Lagrange's equations. That's the basic idea here. And the thing that is hasn't been talked about yet is the explicit independent variable dependence with respect to time. I need an extra term here in general, because a Lagrangian and a Hamiltonian will be functions of coordinates, and then either velocity in the case of Lagrangian or momentum in the case of a Hamiltonian, and time. Now, what explicit time dependence? So what are we really talking about when we put this in there? That's something I need to discuss, because it plays a major role in how the equations come out. Basically, what we're doing is we're saying that I'm going to have something that determines energy, but it is going to be varying with time. If I have an explicit time dependence, I'm going to go in there with my fat little hand and do something to the mass that otherwise would be flying a nice free orbit. I'm going to apply an electric field that's varying, or I'm going to make a magnetic field that's varying. I'm going to do something to need a partial derivative of L with respect to t. That means hold everything constant except time, and I get something that's not zero. Okay? Now, in this case, you see we're writing the chain rule as a time derivative, a total time derivative. So the dt is here in the denominator of the differentials that go with the first two variables, first two class of variables. So the sum over all of the coordinates in however many particles, however many dimensions each particle has, or levers or solids or whatever. These sums can be very long for a complicated classical problem. But I have a dt in the denominator here, here, and here. I don't need that. I just have a partial derivative with respect to L in respect to the time there, with nothing after it at all. Okay? So I'm saying, here's a cartoon to show a mad scientist. I guess I'm considered mad by some people. I wouldn't do anything this mad, though. This is reducing class size by reducing the size of the students and turning the knob forwards and backwards to just get the right size students. So I consider this a nice cartoonish way to imagine explicit time dependence. Somebody, some crazy mad scientist is turning the dial as the system evolves. Another way to get this is to realize the coordinate system is actually moving, like the one we're standing in, the Earth. It's not moving very fast, so we usually say, oh, you don't need to do any time dependence there. With the Coriolis force, that occurs for weather, we just talked about that, so yes, that's important. And so very often you can treat Lagrangians and Hamiltonians as having explicit time dependence just because they're being on something that rotates. And make it even worse, you can rotate it non-uniformly, oscillate it or do something like that, shake the glass. So this term has to be discussed. Now, the reason we haven't discussed it yet is because this equation, this force equation of Lagrange that we got first, which I call the four-wheel drive garbage truck, you take grab anywhere. It works for moving coordinate systems as well as stationary ones. It's just that you've got to figure out what the forces are in the situations. Okay, now it's where we said we were going to derive these things from Lagrangian. Here they are. Here's the definition of momentum, our first Lagrange equation, sitting right there. Here's the other one where I take the dot off of the Q and stick it on the P. So that's as much as Lagrange needs for most of its work. And therefore, I'm now getting a Lagrangian that's written in terms of, well, generalized velocity and generalized acceleration, you could say. And P dot for just the plane velocity, and a P for the acceleration, a double time derivative of the coordinate. And that very nicely folds into a single derivative of a product. Derivative of U times, well, A times B. Derivative of A times B plus B times derivative of A. Okay? And we are about to derive the Legendre transformation from Lagrange to Hamiltonian and back again. Okay? So what's happened here is you take the partial derivative of L with respect to t, switch it on around the equal sign with the total, so that you have a ddt of L minus this on this side of the equation, then you have minus partial derivative of L with respect to t inside this on the right side of the equation. And that is the total time derivative of L. So the total time derivative is equal to the total time derivative of this thing plus partial of L. Okay? That's kind of neat. That's really an accomplishment. This is the Irish side of mechanics. Okay? I think Lagrange knew about it, but it's credited with Hamilton, and it really has some neat features which we're going to try to show. First of all, it's the Legendre transform. Then you know I can switch H and L, right, just like we were talking about when we sort of using hand waving, we drive, quote unquote, this result. Now it's solid, okay, very solid. Now, you see this being the Hamiltonian, there's something really neat that's happening right here, and this is why Hamilton equations are often associated with symmetry and conservation. If it happens that I'm not doing crazy scientist, not turning the knobs, have no partial explicit time dependence, this is zero, then that says the total time derivative of this quantity is zero. So this is another conservation law, different from the ones we talked about over here, where we had a situation where the angular momentum was conserved if the potential had no dependence on that particular coordinate, in this case the angular phi coordinate. Having no explicit dependence in that thing led to a momentum that goes with it, that's this p phi here, whose dot, time derivative, will be absolutely zero. That is, it will be conserved number or function during all motion due to the potential there. Okay, so this is just saying that if you don't have any time, then time's another coordinate in relativity, right? Another dimension. This is sort of just a cousin to that relationship, but in non-relativistic mechanics we treat this very differently. And as we'll see later, this is the total energy for many, many situations. So that means energy conservation is being derived here. and momentum conservation was being derived there. Remember how this course started. We got momentum conservation first, then we derived energy conservation later. It's more or less in the same order of logic here. Now let's look at this in a little more detail with some other dependencies. Recall that the partial derivative of the Lagrangian with respect to momentum absolutely forbidden to be anything but zero. No explicit dependence of L on P. Now that's a very, as we've shown, deep and a little bit hard to understand relationship. I said it's really due to wave behavior that's not known by a classicist. And then the Hamiltonian, just the opposite, its partial derivative with respect to velocity, q dot, identically zero in the same way. So I can go through, as we did when we were playing with the ellipses and things, and take a partial derivative with respect to p of this thing. And I can go through and also take a partial derivative with respect to q dot. Now there are a couple of things I should keep in mind when I do that. And that is, let's take a look at this one, where I take the partial derivative of the Hamiltonian with respect to p, okay? And that means I get a partial derivative of this thing with respect to p. Well, that's just q dot, partial p with respect to partial p. And then the partial derivative with respect to p of L, identically zero. Okay? That's Hamilton's first equation, which we've already seen. The velocity is defined by the partial derivative with respect to p of h. Okay? So that's coming directly from this. Okay? Then we can play some more games. We can say a partial derivative of p with respect to q, that's identically zero. We treat our momenta and coordinates as being independent of each other. I place the thing somewhere and then give it some momentum. Same way I do with Lagrange. I place it somewhere, give it a q, and then I also give it a kick or velocity. So that's identically zero, just as these are. Okay? So you should know that dependence in all of our mechanics. That's an understood physical dependence. So when I do a partial derivative of h here with respect to q, I get a really zero squared. Okay? I get 1 0 from the partial derivative of that with respect to q, and I get another 0 with the partial derivative of that with respect to 0, the velocity with respect to 0, and the momentum with respect to 0 to q is 0. Okay? And then I'm left with a partial derivative of L with respect to q, and a minus sign. And so this partial derivative with respect to q is momentum with a minus sign dotted. Okay? So the change in momentum with a minus sign is thought of as force in everything we've done so far. So the partial derivative of h with respect to qm is kind of a force. We'll see how that works out, but there they are. Those are the two equations of Hamilton in all their glory. Well, not quite all their glory. There's still this issue. A most peculiar relation involving partial versus total derivatives. Very peculiar. The total derivative of this thing is just minus the partial. So we can figure out how much he's changing the Lagrangian, put a minus sign on, and that's how much your energy is going to be changing. Pretty cool, huh? So these are all nice, beautiful algebraic equations, but the physics behind them, I think, really makes them beautiful. So we came from Lagrange to Hamilton with these steps, and they're all algebraic, but we have some idea what the geometry of this is too, and we're going to explore that some more later on. Okay. At this point I should stop because this is the end of the class as far as deriving equations that most people know. Still have Hamilton-Jacobi. We'll do that in the lecture that follows this one. But this is a landmark. We're at the continental divide, so to speak, of the course. And we're only in the review section. Okay. We do this all over again in Unit 1 and 2, but we're going to go through that real fast. And you can catch up by reading. And anything that's not talked about here will be picked up there as well. Okay. Well, we need to come back to that issue of being explicitly a function of momentum. And we also need to make connection with the GCC kind of equation that we had for the Lagrangian up here. We need to look a little bit more on how that plays out with the Hamiltonian. And get used to fiddling around with tensor algebra such as this. So, as I say, Hamilton prefers a contravariant metric because he's using covariant quantities, these intensive variables as opposed to extensive, you could say. So we're going to use the Legendre transform to take the Lagrangian, which we've found to be kinetic energy minus potential energy for situations that were driven by a potential and not necessarily by a mad professor changing the class size. But anyway, with the covariant metric definitions we have here of Lagrange, we're going to derive by using this relationship between the two to get a quite different sort of thing. So here's roughly what we do. And we do this several times for some pretty weird Lagrangians and Hamiltonians. Sometimes we get the Hamiltonian first, we got to go back and get the Lagrangian. We'll do that in good time, but right now it's trying to understand the H a little better. So I go ahead and I write this thing with PM here, and that's this momentum here, which is defined by Lagrange as the partial derivative with respect to velocity. And when I do that, of course, I get the mass times this metric sum here. This is a sum over the ends in general, but in our case, we don't have a sum because our metric coefficient is diagonal. But let's just pretend we do and carry this through with that algebra and get used to working with equations which have implied sums due to an index appearing on just one side of the equation. And to be really strict with my tensor analysis, I shouldn't, it's probably bad form in any way, to use these repeated indices over again in this sum. But as long as you realize that it's okay, and I'm going to be placing this equation in there and getting something that looks like this. Now, this illegal dependence here, we have now written the Hamiltonian as a kinetic energy plus u, okay? And this is numerically correct, but only numerically correct. This doesn't have the right differential behavior. I need to get this in terms of the momentum. And so I invert this metric relation. I do that using the contravariant metric. So I come through and I multiply, and these are details that are on the next page. I just want to show you what comes out first. I go through and I replace each of the Q dots by a GMN PN summed over N. And then I do a similar one for that with different indices so that I don't get mixed up in my sums. And those details are shown next. But this is formally and numerically correct. So red light here, green light here. This is what we need. We need to have this thing in terms of momentum. And that's going to keep you right all the way up through quantum field theory. If you don't do this, it will be wrong for the most elementary problems you do. Okay, here's just some details on the metric algebra. Metric tensor symmetry applies. You always have, even if they're off diagonal, they're equal across the transposing across the diagonal. So I'm replacing each of these guys here, replacing this one to start with that, and then I have another guy right here. And you notice when I stuck this thing in there, I put a different, something to indicate that this end is a separate memory. If we were doing this on a computer, I would have a different memory to keep track of that particular term than was keeping track of this one. So what I end up with here is this GMN times this one, and they're inverse of each other. This is the metric inversion symmetry. One of them transforms you from covariant to contravariant, and the other one takes you back. Together, this product summed over M in this case, that's the repeated index on this side, gives you a delta function. 1 or 0, depending on whether these two ends are equal. You get a 1, a 0 if they're not. So I'm left with this thing plus this thing. This is kind of looking like that thing was in the Legendre, momentum times the velocity, where this Q dot M is given by that inversion relationship. Okay? This is the Qn using a sum over M, that's the Qm using a sum over N. Okay? So this kind of stuff you have to learn to do with a lot of different coefficients when we get involved in the really hairy stuff involving the Christoffel and Riemann equations of motion. That's the real German approach to mechanics. So we've got French, Irish, and pretty soon German. We're using the German stuff right here, really, already. Okay, so there's an equation which I can replace the Qn dot with this thing. And I have here a combination of Pn and then a metric coefficient with this upstairs, and that becomes this. So that's the basic idea of getting this equation right here. Okay. So there's Hamilton. There's the Lagrangian. Okay. Difference in sign. Difference in what they're dependent on. Difference in covariant expression with contravariant metric. This one just the opposite, covariant metric with contravariant kinetic variables. Okay, so our polar coordinate Lagrangian looks like that. Already looked at that up there. This is the polar coordinate Hamiltonian. Okay. Now you might say, do I sum over the R here because I got repeated indices? Well, no, because you've got the variable on both sides of the equation. So that's not what's going on here. We're just multiplying the diagonal components for this. So instead of R dot squared, we got PR squared, but we got, instead of M over 2, we got 1 over 2M. Same thing over here, we got 1 over 2M R squared, instead of just plain old M R squared. Multiplied by half. Okay? And most important of all, we got a minus sign for our potential here, we got a plus sign here. Okay? Now the good question that we're going to try to answer next lecture on Thursday is, okay, you've kind of shown already that the Hamiltonian, which is the sum of kinetic energy plus potential energy. It really fits with my sophomore physics, my elementary mechanics, and gives me what we call total energy. What the hell does this thing measure? Okay? Well, it measures that secret heartbeat that quantum mechanics has given to every bit of matter. It's measuring the frequency that's associated with mc squared. So this is not something that you can explain to even Lagrange, perhaps, but I get the feeling that as the physics was starting to advance, that he had, certainly Poincaré had ideas that there's something really important about what the Lagrangian measured. And we'll go into that on the next lecture, Thursday. But for now, I just want to get the algebraic details and the basic mechanics, an example of the Hamiltonian network that we can compare a little bit, anyway, with our Lagrangian stuff over here. So our next step here is just do a polar coordinate example. Write all the stuff out. See what it is you have to do. What has to be fed into what. And if you're expecting some real help in doing an algebra of a mechanics problem using the Hamiltonian, if you're expecting it to be really convenient, I'm sorry. The Irish method is often less convenient than this to getting equations in motion. But it does have this advantage. The computer solution, you could fix it if you had just a general routine that you would just feed it a Hamiltonian and it would go, you see. And in other words, you could hardwire Hamiltonian motion very nicely. And we've done this with a few things. I almost always find reasons to look at Lagrange's stuff first, but this is some point I want to make before we're finished here. Okay, this is writing out our 2D polar equation and looking at the first equation and the second two equations each, just as we had for Lagrange over there. Okay. So the first one involving the radius is that. One involving the angle phi in polar coordinates is that. Okay, so far so good. Right? And there are two for this one. Partial h with respect to the radial coordinate is minus the momentum change, rate of change, total. Phi, same thing. Okay? So far we're not getting all that much. Okay? But then we can go back and look at the Hamiltonian and say, oh, what is the partial of h with respect to PR? That's easy to do. Okay? We got 2 PR for a partial derivative, nothing from that. Then the 2 cancels the 2 and we end up with PR over m. Okay, remember from over there the PR is m times r dot, so this is just going to be r dot. That's not too surprising. This one, a little different, okay? This one's giving us that the partial with respect to p phi. It's inverse inertia on p phi, okay? This one a little bit more robust, and this is, we'll work with this to some extent here. Partial derivative of h with respect to the radius. Well, there's a radius here, and there's probably radius here. This thing's usually a function of a radial coordinate. For central forces, it's what the only one you have to worry about. This one you don't have to worry so much if you don't have any bumps around things. This isn't a dipole or a quadrupole or an octupole potential, just a monopole. You won't have any of that. So this guy right here, this partial h with respect to phi, will be 0. That will again give you a conservation of this. You see, so you're getting conservation laws just like the one over there here. Okay. Well, as I said, P comes out m r dot. when you're done with that. Let's see if there's anything else I can point out here. Yeah. This one comes out P phi equal mr squared phi dot. Okay, that's good. We got that immediately over here, just in the section here where I said wow. We got that pretty immediately. Okay, that's checking. These twos cancel and give us a kind of an interesting relation. Not one that rolls off your tongue, but there's a radial dot equation involving the square of the momentum and then a cube in the denominator. It's kind of already we're going and getting something we didn't get directly over here. Everything that happens here should agree with what happens over there. This one, these being pulled down now from above there, using what we've got, okay? This tells us that P dot, angular dot, is just going to be minus this derivative, which we would only have for higher multiples than 1, okay? Now, at this point we do what we did over there. We find P dot directly from a time derivative, okay? So I can immediately stick that in there, take the time derivative of this and get basically Newton's equation in a radius, okay? And this is the P dot R that we're talking about up here, and that comes to be that. Changes sign because of this sign. Okay. And this one, P dot phi, now you have to go through, and everything that can change in here has got to be differentiated. Okay, that, and using this and this, we can make a relationship for P dot R in terms of the phis and the potential. So you see the equations of motion eventually come out as P's and P dot phis in terms of things that we were using over there, velocities and coordinates. But you see, it's more messy. There's more stuff that we have to do than over there. The algebra is more extensive. But I recommend, if you have a chance to do it, if you're doing an equation that's fairly complicated with things that you're unfamiliar with, you check the Lagrangian results with the Hamiltonian results. You'll be error-free if you do that after you've done it. You may not be error-free with that. You're less likely to be error-free with this, but they have to jive. Okay, and I want to point out the Runge-Kutta business. Here is Runge-Kutta formed. We've got radius, we've got momentum of the radius, we've got angle, and we've got momentum of the angle. And we've got equations for the first derivatives with respect to time, total time derivatives, of them all, in terms of the variables that we're working with. If you have this form, you're good to go. Then Runge-Kutta, of whatever order, there are all kinds of different correction routines and all sorts of things that we've torn our hair out getting to work. And we're going to be demonstrating some of the older ones in the simulations we look at. But that is your ticket to the workhorse of numerical analysis for mechanics problems and a lot of other things like quantum mechanics problems. Now I would like to look at the effective potential idea and then do a simulation that shows it. And I'm going to do this first for the oscillator because we already have worked the oscillator to death and we have a pretty good idea what its solutions are in Cartesian world, but this is in polar world and it's quite different in flavor from what we did before. Now we're really taking advantage of the radial coordinate. Polar coordinates, really. And we know that we don't have to worry as much about the angular coordinate because this thing, this p phi here, is constant, conserved. So we're going to be able to rewrite this on the basis of the symmetry. The idea is that as I go around the angle, I encounter no lumps in the potential. And if there are no lumps, there are no bumps. Bump is momentum changing. No lumps, no bumps is what that's saying. That's a really crude way to say Noether's theorem. Emily Noether is a famous woman mathematician, physicist, who went another way to get the Hamilton and Lagrangian results. And supposedly people think it's more general than that. It's more or less some truth to that. In any case, because this is 0, I can just call this something, a letter script, or italic L is a favorite one in quantum mechanics for orbital momentum quantum numbers. We're just using it here as a constant to rewrite the Hamiltonian. And the Hamiltonian, remember, is constant because of the no explicit time dependence here. We're not changing the mass as this thing goes. We're not changing the spring constant of the oscillator as this goes. We'll do that, a little bit of that later on. That's called parametric amplification. The main thing is this thing right here has given us a term that's just the inverse of this one. It's kind of interesting, I think. So we really have a one-dimensional problem now. So let's finish the one-dimensional problem and then simulate the whole thing. The basic idea is that the energy now is a kinetic term plus an effective potential. Now the real quote-unquote potential is this one, presumably given by either a Coulomb law inside or around a charge, or gravity affecting our inside of the Earth, sophomore Earth problem, which I would say is also effective. We don't really have a feeling for what's causing it. We just go ahead and say, let's work this and have it come out and see what it gives us the right answer. But in any case, this one is due to fictitious forces. The Coriolis and centrifugal forces are all working together to make this one. So it's a very simple description of some pretty complicated stuff that we call Coriolis and centrifugal motion. But it's given a name. It's given the name centrifugal barrier. That is, it's something that's going to put a big barrier up for getting R small. As R gets smaller and smaller, this thing's going to go up quadratically, inverse quadratically. And so it's going to keep the particle, or whatever it is that's described by this energy, from ever actually getting to the origin, to R equals 0, in order to keep energy constant. Okay, so that's a, this technique is a very nice technique. This is a very famous example of its application. So what we can do now is we can solve for the radial momentum. We don't have to do any integration at all at that level. I can just go there and write. Now I left out the plus and minus R. We'll see why I did that, because they sort of happen together. This is just the positive square root of that term with, in our case, an isotropic harmonic oscillator potential Kr squared over 2 as potential. Okay? So this is giving us now the total time derivative of the radius. And we're only working with a radius. The angle is out of here. We're going to see it come back in the simulation. But as far as we're concerned, angle doesn't exist. We're riding around on something, and I'm just looking at the distance to the object in question. So, taking the square of the square root, I can write the radial kinetic energy that way. Now we're sort of doing Lagrange stuff by looking at the velocities, and then there's the velocity written out with the without the plus and minus, and then I just do time integral of that. Now this in unit 5, we're going to take the two problems, the oscillator and the Coulomb, apart simultaneously, step by step. There's really some interesting stuff that you learn by just doing that really carefully. But in any case, this type of solution for any potential UR, here we've got the oscillator, KR squared over 2 as a potential. We're twice that, so there's no 2 there, just a inverse M. That integral, in general, this sort of thing, when you get the problem reduced to this, it's called being reduced to quadratures. This is jargon, okay, that you hear a lot. I've reduced the problem to quadratures. What does that mean? I'm doing a quadrature integral. It's called a quadrature because it's a quarter cycle, a quad quarter, okay, solution. If the integral independent variable starts at, well, and this sometimes can be difficult, as I've pointed out here for Coulombs and various things, but in any case, if you start with this thing at 0 on, I should be really talking about angles that go with this thing, but in any case, when you start this thing off, you start with, say, some minimum amplitude and go to some maximum amplitude. If it's an oscillatory system and you're going from some minimum, say the perigee, and you're going to shoot the thing up to the apogee, that will be, in some sense, a quarter of the orbit. Certainly will be for a Coulomb. It will be close to that for any other orbit that doesn't close nicely like a Coulomb or an oscillator. So this is sort of trying to give you some reason, as much as I can tell, why this is called quadrature. So this is the end of the algebraic description. What we'd like to look at is how it plays out. So I'm going to play out the picture. It's not an app yet. It's just a Macintosh application. I got the old Macintosh there. Hopefully you're going to run it for us. But what you're seeing there is an actual plot of the, first the real potential. This is the oscillator, isotropic oscillator. Every direction has got a parabola like this as its potential. And that's KR squared over 2, the real potential. And then the effective potential that has this barrier erected, you see, this barrier where these things just go whooping up to infinity as we approach 0. That one depends on this constant right here. Mu here is L squared over 2m, roughly speaking. So, in fact, I think actually this mu here is exactly L, but yeah, I think that's right. In any case, if I don't have any angular momentum, I can just cruise right through the origin. And I just oscillate back and forth, say like in a tunnel inside the sophomore physics Earth. But if it's got any angular momentum at all, in other words, if you aim the thing at any angle with respect to the radius, so you're not pointing at dead center inside the Earth, you're going to get an orbit like this. And so what's neat to see is how this works. The perigee is a turning point where the thing comes falling down from the thing, gets to the lowest orbit, okay, turns around in the radius and it goes back out. So this is a turning point in this picture, but it's you got to remember that this picture has got to be rotating with the radius, you see. So that makes it a little bit complicated. And this is just the oscillator. We did the oscillator so easily with Cartesian coordinates. This is pretty complicated. So I'm going to try to play this. If you want to shift the view over to this, we'll look at a couple of things with the oscillator, and then you already see that it's going to make an ellipse that's nicely centered, but it's also one that is, let's just let her rip and see what happens. That's what I don't want. I want it in color, but there is the orbit happening. Now, one of the first thing that your eye catches is that this has got a frequency of going around the loop, but whatever this thing is doing is twice that frequency, right? So it's apogee, perigee, another apogee, another perigee, you see, in this oscillator, okay? Now, this program lets you play with this thing in the sense that you can actually move potentials and things like that around. I can drag this guy up to here and just sort of drop him off at no place. But what I'm going to be seeing, you see, is a very different orbit. And this one's not lined up like the other one was, but that's the point. You can start it anywhere and let her rip. Now this thing is stable, you know, it's always going to be stuck somewhere between these points. Or I can try this, I can try to make the thing so that it's not moving. Well, it's kind of hard to do, but what I'm going to do is I'm going to split the difference here. It's about there. And I think I'll get a pretty good circle. Okay? So when you're at the lowest point on the effective potential, and that's the trick, is to find out where that is, because where this technique gets used is to figure out all sorts of weird oscillations that are completely anharmonic, but at least for small oscillations are harmonic. So oscillations around that circle could occur for a potential that was much different from this one, but the frequency would be different when you got off of that. So if I go up here and just pick a given velocity, you see, I can make my velocity set the effective potential. And of course the problem is that I immediately draw stuff all over there because it's an XOR routine. But this is a higher centrifugal potential now. And its equilibrium position presumably would be about there. So it would correspond to a circular orbit, and that's not circular. It's really hard to sometimes get the thing in the center there. And that's pretty good right there. Oscillating more than a pixel. In fact, I don't think I'm even doing that in this. Now this is where the new app for this one would be able to do you know, much more careful analysis of things like that. But let's just go ahead and erase these paths. There's where we're stuck right now. Okay? So that gives you some feeling for how an effective potential really works. It's always following the radius, right? And that radius isn't uniform, usually. Okay? Here it is. When you're in a circular orbit, the angular motion is uniform, right? And the r is constant. But if that r moves at all, then the angular has to change because the moment of inertia is changing, right? As you pull the mass in somehow, it's got to go fast. As you let it go out, it slows down. The old skater pulling arms in to do a pirouette. So now, just for the sake of argument here, I've got to get the right mouse here. Let's stop this. One of the things that we'll be able to do with the app, and I'm going to do it right now with the dynamic parameters, is I'm going to let it plot, phase plot, okay, and see if it gives the right kind of momentum curve, as well as the orbit in the radius, okay? So I do an off-screen animation now here, just like the one we're doing, and you can see that I get a PX-PY momentum ellipse. And as I try for other, say an ellipse that's like this, it's real close there, has a barrier that's going real steep at the initial part. Apogee, perigee, apogee, perigee, apogee. I'm getting the same sort of thing here in PX and PY. Getting really fast Y and so forth. So this is kind of a nice example. Now, the phase space for the radius is kind of weird, and we'll study more about that later on. As you get skinnier and skinnier ellipses, let's just do one out in the middle here. Boom! Boom! Okay? So you get really aberrant radial behavior as you do the jump. You see the gallop right through the origin there. Boom! Really change your radius quickly. Your derivative of your radius. So the radial momentum is proportional to r dot, and you're seeing it do a jump there. Meanwhile, this is pretty well behaved down here in the Cartesian components of momentum. All right, let's stop this. Go back to the parameter changes, which we'll have in the app supposedly. And I'm going to drop back here to a Coulomb potential. This is outside the sophomore physics Earth or any massive body. I'll leave the phase plot off for a moment and set this up to do a Coulomb. Let's see what happens now. Maybe flame and smoke come out of this old computer because Coulomb has got a singularity of its own. There's the real potential there, and the effective potential you see is not too distinguishable from what we had here. It's just that it drops below the axis for all of the stable orbits that are possible. I'm going to come back here now and look at a big picture with some annotations for the Coulomb orbit. It's Hamiltonian dynamics here for a real potential of minus k over r. It has to be attractive, or this isn't going to work. Got to be able to go negative. And the effective potential, which is the sum of that negative, and then something that goes very positive, and then something that's always positive, momentum squared. And we're looking at roughly what's animating over there. Okay? But now what you see is you've got one apogee as in upogee, and then perigee, the opposite of that is the closest approach, the down. You got one up and one down for the whole orbit. So there's a difference in frequency, you might say, between the potential that we have here and the other one. Almost twice the actual orbit frequency. And we'll see how that comes about when we get to Unit 5. You can go ahead and read ahead to see that. But there's a lot that I've discovered since I've been teaching this that is included in the lectures and not in the textbook as it's written right now. So anyway, I do the same thing. I can find a stable region here. It looks like it's probably about there. And again, it's awfully hard to get right in that little well there. Let's see if I can do it. It looks pretty circular, but you can see it isn't. This thing is still jerking around there. I can do something like this. I can go out there until I'll put the thing at a pretty close to a minimum, and I should be able to get a pretty good circle with that. Well, it's not terrifically circular, but good enough for government work. Anyway, you see there's quite a difference between these two examples, inside the sophomore Earth and outside the sophomore Earth. Let's stop this and turn on the phase plots, see how they look. The Coulomb phase plot is remarkably simple, although has some surprises. Let's go ahead and get it going. It has a very jumpy radial phase plot, but look at the Cartesian momentum plot. Isn't that something? No matter what I pick, I can pick some pretty bizarre orbits. I always get a circle for the plot of the Cartesian momentum. Well, it looks that way. We'll prove that by geometry when we get there. But I think that is really quite remarkable. So no matter how I start this orbit off, when it came to the oscillator, there's a really big circle. It's gone off the screen on the bottom there when it's passing the perigee. Boom. Okay, Halley's Comet comes in. Boom. But its momentum is making a circle. And it's not uniform velocity around that circle. I can, of course, try to produce a circular orbit by doing this thing again. I look like I don't know what I'm doing here because I'm having a hard time finding the momentum, the minimum rather. But if I have a very nearly circular orbit, then you would expect I would have a circular momentum orbit. And yes, I do. I didn't do anything funny there. Okay, so this gives you, I think, a pretty good feeling for how an effective potential has a lot of, it hides a lot of sins, but it also hides a lot of beauty, and shows it if you can animate it. We talked about the two of them together. This would be a situation where I had an Earth that actually stopped somewhere, say wherever. We still have the picture of this potential on the board here. I didn't intend to have this as the longest I've kept one of our drawings on the board, but if you just take a look at our outside the Earth potential, which at the surface of the Earth, that's 1 in this geometry, R sub Earth, becomes a parabola that goes down to here and has 3 equal levels to escape. Escape being whatever it takes to make the angular momentum of this thing go essentially to zero as I fly away with minimum amount of energy to leave forever, that is, go to radius rho, in this case is a symbol, to infinity, to escape, as it were. So we have at the bottom of the potential for the Earth, and then a jump of energy just to get back to the surface but not have any kinetic energy, just potential energy. And then another jump to get into an orbit at that radius. That's a skimming orbit, the minimum orbit velocity to be in space orbiting the Earth. Okay? And then the same amount of energy to leave. So you see, there's only a factor of 2 between minimum orbit and energy to leave, escape. So just to remind you of this 3-step picture of dynamics for the combination of the oscillator and the Coulomb that is that sophomore Earth model. Okay, we're getting a little close to the end here. That is in time, so we might say a couple more things, but remember this when we go back later on in Unit 5. I can make some envelopes here. I'd like to show you a couple of things that are sort of hints to problems I'm going to be giving you fairly shortly here. This is the envelope that involves the fountain of ejecta on Io, or the fountain in the tiny little fountain that occurs inside the chambers at the National Bureau of Standards, the National Institutes of Standards and Technology, what it's called now. And the idea of this family of orbits, and also a family of circles, I'd like you to take a look at that. And TC, maybe if you want to go ahead and use the modern version of this.
Start film.
And I've just goofed it up for you by making the thing go off the screen there. Let's see if it comes back. Quickly enough here. Later on.
Skipped it.
Oh, I'm sorry. I don't have to do that. I nearly have to throw a switch here, I think. There we go.
Yeah, it sensed it.
I forgot we're dealing with 2 computers. Go ahead and you're quicker than I am of bringing up Coolant, which lets you look at oscillators and as well as the Coulomb orbits. And let's look at the oscillator. Well, go ahead and look at the easy one is to look at the fountain, right?
Okay, we'll load that one up first.
Yeah.
Labeled here is parabolic fountain.
So go ahead and you might set the number of particles that are being ejected to 50 or 60 or 70 or something like that.
There's 70, that sounded like a nice figure.
Yeah, that ought to be good. Now this is an app that you guys can play with, and there's all kinds of things that happen there. But there's the ejecta expanding as a ball, and then that ball, once it reaches the top, has 2 tangent points to the orbits. And right now, TC has the feature that plots the Lagrangian's value in color, which is the phase value. So you're actually looking at a quantum fountain in that picture. That's a little bit distracting, so maybe we just go back to one color on that, look at it again.
That has been a bit, just make this 0.
Yeah, make it 0. I think that'll do it. I want it Yeah. We'll let it, so that should be, oh, I think I see some color there.
Oh,
It
let's
doesn't
put
matter.
two.
You'll still get the idea of
Right.
where the blast wave, which on this screen right here, is this circle, the blue circle, okay, has to be a contact point for the actual parabolic orbit that goes with that. That's this green curve right here, this parabola going, I'll follow my finger here, from a launch of alpha equal 30 degrees in this case, touches at that point. And the idea is to see two of the kites here. One is the kite of that particular green orbit, which is the green kite that comes up and stops right here at this point, which happens to be the focus of, not happens to be, but has to be, because that's what this kite is giving you, is that corner of the kite that goes along here. Okay? And then that point right there has to be pointing at the focus of the entire envelope in order for us to have a contact point. And this is really a neat way of seeing how these things are all tied together. The circle, the parabola trajectory, and the parabola envelope of all trajectories has always that kind of relationship. And the other thing to see is as you change this angle, this focus of the individual trajectories is on a circle. Obviously, starting at the top for a trajectory, this goes straight up and straight down. A parabola is completely degenerate. But all of the others have this. So you have a green kite here inside a congruent kite that is, holds for the envelope and that particular contact point. Now, let's maybe switch over to the oscillator, which is the way to get that, I think, is to go for the explosion. The
Maybe a little more.
yeah, and go ahead and just click. I don't know what it will do now because we have been messing around here. Let's see.
First comes to where she just refresh.
Okay.
There it is. Default.
Yeah, and then go back and pick up the space bomb.
That's what you were segueing into.
Yeah, that will probably be it. Yes, there you go. Now, this is something we will talk about later, but if you have a bomb go off outside of a, say, a neutron star or something, we're making all of the mass of the things that these are orbiting around be down there in that blue hole there. It's not a black hole, it's pretty dense. And you see that these things bounce off each other and then recover, and each of them goes on their separate orbits, and some of them go very close to the blue hole, and they do it sort of twice, and then the whole thing recovers. Okay, this is really a neat thing. What I'm going to ask you to do is do some analysis of the oscillator, the harmonic oscillator, which is the starlets inside the Earth. So let's go ahead and just start this thing again, but this time with the Coulomb replaced by, that's Coulomb -1, let's replace the, yeah, we can do that. We can make a nucleus have a charge.
Well,
It's probably best to pause the thing while we're doing this, because you can see it really blew there.
so I'm not quite certain where we're headed.
What we're going to do is do the same explosion, but with the potential equal to, let's see, you've got Coulomb is -1 right now, so set that to 0. I guess would
Let
be
me just
the,
restart. Space bomb. And you're saying change something?
Yeah.
Change this to,
We want to make, instead of let's see, what is it?
that should go to 0, and then I should switch to diamagnetic
Yes,
strength.
that's the way you did it. It's sort of a cheaty way to get a spring constant, right?
Right.
So
Even have the K.
go ahead and pause, because they're going to all disappear from the
Just erase pounds and restart.
yeah. Okay, that's a neat one with a repulsive string. Go ahead and see if it will go negative on you. Yeah, get rid of the Coulomb constant, I think, for this.
Well, if there's no nucleus, we'll be all right. Thickness, just keep on making it smaller and smaller.
That's probably not right. Let's see.
And
I know I've done this on this particular program. I'm trying to think. There you go. I think that's got it. Yes. That's it. So if you're inside the Earth,
With an
same
explosion.
deal. And obviously, if you look real closely where it is right now, that's very similar to the fountains of EL. It's very nearly a parabolic envelope at that point. The ellipse is very eccentric here. But that's the kind of thing that you, see if I've got one here. I thought I did. Yes, this one. Okay. Exploding starlet. The elliptical envelope of all of the ellipses. Yeah, there's another one right there.
You can do similar user input,
Yeah.
drag, initial position, and then
And just let it go. Yeah.
minute of your burst.
Yeah. So this is a kind of mechanics that is very beautiful. Probably people wouldn't attempt it without having a computer, but this has a very simple geometry. You know how when you're given an ellipse, to find the focus, right, you take a compass and strike an arc, and right there, where it crosses the main axis, is a distance equal to the semi-major. Okay, those two lines between my two fingers are both equal to A, which is the semi-major axial distance, or major radius of the ellipse. Okay, so you have a here and a B here, and then you have a square root of A squared minus B squared as your focal distance. We're going to study all of that stuff and use it later on, but here's a case where the thing explodes and makes an envelope like that. And the explosion points are at the focus. Just like the parabola case, the ejecting point is at the focus of the envelope. So those are all kind of things that are quite apart from the study of the algebra of all of this stuff. This is what I would call the beautiful part of the mechanics. A mathematician, of course, sees beauty as well in the formalism. Now, after this, and I'd hope to do this today, after this we need to look at the simplest Hamiltonian and actually plot that thing and study that. I hope to do that today. That will have to wait until Thursday, but I think we can easily fit it in then. So I would say we are at the end. Are there any questions that you need? Been very quiet today.
Yeah, because
The algebra is...
yeah, just need to read the text and just work out the algebra.
Well, of course. And the sooner you do that after a lecture, the better, because it sticks better.
I
And
can't do
neural network.
It's a form of repetition.
I
Yes,
can't do
it-
too much of math in my mind. I need to work it out on a paper.
Yeah. Sure. And I'm sorry we don't have the apps, all of the apps that we need for this particular section running yet, but
Dr. Harter, whatever you discussed today, is it still in chapter 12? Whatever you discussed today?
this is
Chapter
all this
Uh,
is definitely chapter 12.
of unit 1.
Yeah, the last chapter of Unit 1. Yeah.
Excuse me, I have a question regarding ground
Yes.
piece diagram. Can you briefly explain if you can how to draw diagram of one over x?
Thank you, Dr. Harter.
Oh, you mean an actual geometrical
Yes.
construction? Yeah.
So that's it.
Let's see, probably the best place to look for that, there was a description in the, and now I'm trying to figure out which lecture that was
Let me
in.
reference it for you.
I know I can find it right away in the textbook, so
That's
that's what
interesting, Dr.
I'll
Harter.
do.